Maybe. Just let me know. It started. All right. Well, hello everyone, and welcome to MathSoc's Math 3411 Revision Seminar Part 2. Yesterday we had the amazing James Kirkpatrick teach Part 1, and then I headed up Part 3, Section 3 of the notes. And today we're going to do Sections 4, 5, 6, and 7. So I'm going to be taking you through information theory, and then Cyril is going to take you through number theory, algebraic coding, and cryptography. Alright, so before we start information theory, we're going to go through, we're going to go through entropy, Shannon-Fano coding, Shannon source coding theorem, entropy of Markov sources, what the hell a noisy channel is, and what channel capacity is. Alright, so we don't have an infinite amount of time, but hopefully we should be good to go. As always, questions in the chat if you have any. And let's get started as soon as I get down to where we were. Alright. Yep, and hello. Welcome. Alright. So, that's 3 LZ78. Is this information theory? It's information theory. How lovely. Alright, so, information theory. Let's start off with, well, the name of the game is information theory, so we had better talk about what the hell information is. So, information is just a number that we ascribe to our source symbols. And the number represents how surprised we are to see that source symbol as an outcome. So we could say, hey, for a source S with probabilities 99% and 1%, and let's say we receive S1, that's the one with probability 99%, well, we're not surprised at all. There's no news, so the information is low. However, if we see source 2, then the information is really high, right? Because there's only 1% chance of that happening. It's news, so we call that high information. All right, oops, that is not a finger. All right, so here's our definition of information for this course. For an event with probability p, the information is given by this little formula. It's a pretty cool formula. You'll use it a lot. So I of p equals minus log base r of p. That's our formula for information. Some properties about information is, well, for the probabilities between 0 and 1, the information is greater than 0. That's good news. We can't really have negative information about something. For the information of 2 events is going to be the sum of the information of each individual event. Right? Hopefully that makes sense. If 2 events happen, you have no more information than if the 2 events happened independently, I guess. And I of p is a continuous function. That's just kind of something that we want to say because it'll help us do stuff later. All right. So, entropy. We've defined information, but now we're going to look at the main player of this topic, which is entropy. So, entropy is just the weighted sum of the information. That's really all it is. It's measured in bits, which is going to be important later, just for our intuition. And also the information is measured in bits. I guess that makes sense. If one's the weighted sum of a number of bits, then they should both be measured in the same units. We can also say that the entropy is the expected information per source symbol. Right, hopefully that should make sense. We've seen a lot of entropy, and, well, I'm a physics student, so I get to talk to you about, hey, this is actually, uh-oh, my pen has died. Let me just shake it. But I get to talk to you about how information shows up in physics. But I'm not going to really go too far into that, but it turns out it's the exact same formula. That's all I say about that. Okay, well, this pen has actually died. Alright, we'll use this battery. Hopefully no issues. Alright, so something more about entropy is that if we have no subscript, we can assume that it's radix 2. That's just something that we're doing in this course. If we need to remember what radix is, we had a lovely revision seminar yesterday where we went through all of that. Alright, question. So, the average length, find the average length of the binary Huffman code for a source S with symbol probabilities blah. Alright, so Huffman code was something that we did yesterday, so I'm not going to do it today. It turns out what you do is you'll end up seeing that the average length of this code is going to be 1.6. And we need to compare this to the entropy. So let's calculate the entropy. So the entropy, h of p, or h of s, rather, is going to equal the sum pi log pi negatives. All right, so this is going to be equal to, I'm going to use this because it's probably useful. So this is going to be negative, no, it's not working. Okay. I'm going to have to just flip my hand. So this is going to be negative 0.6 log 0.6 minus 0.2 log 0.2, and so on, yeah? And that's exactly what we wrote down here. Turns out this is going to be 1.57. Now, something to notice is that the entropy, which is like the average number of bits per source symbol, is less than the average length here. And I guess you could say that that's because that we're using a Huffman code, so all of the code lengths have to be integer lengths, right? So we end up, from this example, seeing that the length of some code is greater than the entropy. That'll show up more explicitly a little bit later, not too long. All right, that's exactly what we said there. All right, so this part of the course, there's just like, we start hearing a lot more theorems. Not really much we can do about it, we just have to go through them. Here's the first one. It's called the maximum entropy theorem. It is a result that Thomas Britzer said, hey, you should know the proof of this. Well, what does it say? It says that the log base r of some source alphabet is going to be less than or equal to log base r of q, where q is the number of symbols. Q equals the number of symbols. You might even be able to write that as as absolute s, but getting ahead of ourselves. So, how do you prove this? Well, actually, I'm going to leave that as an exercise, but first, I'm going to go through exactly what you need to be able to prove it. And this is really what comes first in the course notes. We need to be able to have a Gibbs inequality. Now, Gibbs is like a hugely big historical name in physics, but in this course, he's just like this little guy that does this one theorem. So, what does it say? It says that if you have two sets of probability distributions, so that means that the sum of P1 and the sum, oopsie, that should be a sum, not a line, sum of Qi, these are both equal to 1. Okay? So these are the probability distributions. Then we have, well, this looks like the entropy of Pi, which it is. And this is, we're replacing the Pi in this one with the other distribution. And so this is kind of inefficient, and so the entropy gets larger. That's kind of the intuition for that. All right, so the proof of this, I can do a quick outline for you, but it's going to have to be pretty quick. What you're going to want to do is you're going to want to bring this over to the other side, and what that'll end up having, the effect of doing, whoopsies, is it'll have the effect of bringing this down to the following equation. It'll be sum pi log of qi on pi. That's going to be what you're going to find when you bring this over and do your log laws. Alright, I would go through this a little bit more detail, but, you know, time's of the essence. What you're going to want to do then is you're going to want to say, well, I know that ln of x is strictly less than, that looks like not what I want it to look like, it's strictly less than x minus 1, right? So you can see that just by looking at this is a natural log, and this would be like x minus 1. It's actually not strictly, it is exactly less than or equal to x minus 1. Alright, you can do that here, and what you will find is that this hand side is going to go to 0, and so you have proved your result. So we brought this over to the left hand side, so this side has to equal 0, so forth and so on. Can't really do much more detail than that today, so yeah. Look through the course notes and you'll see a much better proof done by Thomas Britz. Alright, cool. Next up is entropy. Oh, no, this is just talking about exactly what I said earlier, where we're just like mixing and matching the entropy with this other distribution and it's making it less efficient. Here's a cool theorem. Again, theorem heavy part of the course. Just going to be going through theorems for a little bit. Consider a source S. Consider a source S with probabilities. Suppose that C is a uniquely decodable code for S, right? That's the important thing. Then the length in that uniquely decodable code is going to be greater than the entropy, right? So this is our first source coding theorem. Proof is a little bit in detail, so again, we can't go through it. It's very unfortunate, but I guess Thomas Britz's notes would be better anyway. All right, so we have, now this equation has equality if and only if pi is equal to r to the minus li, which is just the Kraft-Macmillan sum, which we saw yesterday. Yeah, so in this case, the Kraft-Macmillan sum is equal to 1. All right, so a lot of theorems, but now we get a little break from theorems. We finally get to do a little bit of coding. This is called Shannon-Fano coding, and the way that it works is it's a way that we can take just the probabilities and immediately map them to lengths, right? So yesterday, we had to look at all the probabilities in total, and after looking at all the probabilities in total, we could get the lengths. So that was the Huffman code, yeah? This is one of the advantages of the Shannon-Fano code, is that we can just look at a probability and we can get the length of its code word really quick like that. The way we do that is just li equals the ceiling of minus log base r of pi. All right, so and then after we get those lengths, we can just use a standard radix ri code to come up with our code words. Okay, we saw that yesterday as well, though maybe we didn't state it super clearly. Well, best to go through an example, I think. So, here is an example from a past paper, so let's go through it. We have probability 1 equals 0.4, probability 2 equals 0.2, probability 3 equals 0.2, probability 4 equals 0.1, probability 5 equals 0.1. Cool. The thing that we do now is we find the lengths. So this is going to be the length of ceiling minus log of 0.4, and so forth. What you will find is that this is equal to 1, this is equal to 2, this is, well, it's the same probability, so it's going to be 2, this is going to be equal to 3, and this is also going to be equal to 3, right? I'm just doing those logarithms on each step. Next thing is, well, we've got the code lengths, So now we just have to use our method for finding standard instantaneous codes, which is, we can just draw out our tree. So this is a ternary Shannon-Fano code. So our tree is going to have 3 branches at every node. Yeah, so 1, 2, oopsies. I should just do like one line. 1, 2, 3. So this was 0, this is 1, this is 2, right? I'm counting from top to bottom, because that's the convention that's used in this course, so remember that. So we want one code word of length 1, so hey, we're going to just like call that one length 1. Now we need 2 code words of length 2. Well, I'm going to just draw out our branches from this node. We need 3 branches at once, so there's going to be S2, it's going to be S3, and now we need 2 code words of length 3. And so these are just going to come from here, S4, S5, and we have one other branch that's just not being used. Yeah. All right, so from this we can develop our code words, and what we will see is that our code words are 0, 1, 0, 1, 1, 1, 2, 0, and 1, 2, 1, right? So if we go back up to this tree that I drew, we could have 0, 1, 0, 1, 1, 1, 2, 0, 1, 2, 1. We see that these are exactly the same. Cool, so we've done Shannon-Fano coding. Yay! There's, I think, always a question on Shannon-Fano coding, maybe like a ternary one in the final exam. So yeah, keep your eyes out for that. Here's a cool proof. So back to the theorem part of the course. Sorry about that. We have this result. This is for the Shannon-Fano code. It says that the Shannon-Fano code is, well, obviously, it's a uniquely decodable code, so it's going to be greater than the entropy, but we have an upper bound as well, which is the entropy plus 1. So the Shannon-Fano code is actually, like, relatively decent, right? You're never going to be too far away from the entropy, which is the lower bound for any uniquely decodable code, right? You could also actually say, hey, I'm going to look at the Huffman code from yesterday, and something that you might remember is that the entropy for the Huffman code is less than, or the length of the Huffman code is actually strictly less than the length of the Shannon-Fano code. But this is also strictly greater than the entropy, HR of S. So, although we've just proved this for Shannon-Fano code, you can also say that this applies for the Huffman code. Yeah? That's something that we will... It might show up. I think I saw it show up in an exam a couple years ago. So, you know, just a fact to know, and I'm just going to leave it there for you to be like, oh, I didn't realize I could do that. But yeah, that makes sense, right? How do we prove this theorem? This is actually one of the theorems that we actually do prove in this seminar, because it's a kind of a quick proof. What we're going to do is we're going to write out the entropy. Can I get a time check? Yeah, it's all right. Cool. Yeah, 16 minutes in. All right. So we have that the entropy. We can just write out its definition here. Yeah. So at the beginning of this lecture, we said, hey, the entropy is going to be minus pi log base r of pi, and you sum over all the i's. Yeah. That's just the definition. Now, this step is the tricky step. This step is saying that, well, x is always less than or equal to the ceiling of x. This is the trick in this part of the theorem. And I think this is probably the bit that Thomas Pritz wants you to recognize for the exam. He said that, hey, you're going to have very standard exam. Look at all the past papers. It's going to be very standard, but you're going to have a couple tricks that come from looking at the proofs. So, I mean, this could be one of them. Just looking at, hey, we can make use of the ceiling to come up with the length of the Shannon-Fano code. Right, this is the length of the Shannon-Fano code because it's the weighted probabilities of the length of the Shannon-Fano code. Yeah, sorry, I went through that a little bit quickly, so if it doesn't make sense, shoot something in the chat, and hopefully I will be told if there is any questions. So we've proven this part. now I have to chuck it over to this part, yeah? So we have the length of the Shannon-Fano code, we just do that by definition, is going to be less than, and this actually also comes from messing with the ceiling function. We have that the ceiling of x is less than, this is strictly less than, x plus 1, right? So you can imagine, like, what's the ceiling of 2? Well, the ceiling of 2 is 2. What's the ceiling of 2.5? Well, that's 3. Right, so from these two examples, it should be pretty intuitive that the ceiling of x is going to be smaller than x plus 1. Yeah, because you're always going to hit an integer in between x and x plus 1, and that's what the ceiling is going to evaluate to. Yeah, hopefully that makes sense. And we just put in definitions again, and we get the other side of the theorem. Cool, so we've proven this. Yay, give yourselves a pat on the back if you understood that. And if not, that's okay. We have so much time. So, next up is the entropy of extensions. So again, sorry, proof heavy, theorem heavy part of the course. We're going to go through a bunch of theorems right now, at least a couple more. So, the entropy of extensions says that, hey, we have the entropy of an extension to a code. So remember that was like if you're writing out a code for like multiple different sources for multiple different source words at the same time. That was in yesterday's lecture if we don't quite remember that, but yeah. Basically the idea is that we can bring the n down the front for an extension. I do think that there should be a couple more words here, because we're going to see actually a counterexample to this a little bit later. Yeah, but in general, you have the entropy of extensions for a radix R uniquely decodable code is going to be bring down the n, and that is, yeah, just bring down the n. That's our theorem. We don't need to know the proof of this, we just need to be able to quote it. But we do need to know the proof of is this one. This one absolutely will show up in your exam. It showed up in literally 2016 through to 2019, every single one. So, you know, that's something to make note of. The way that we prove this one is by just taking, hey, this is our definition of how we take entropy of extensions. We use this theorem, take the n's down the front, divide by n, and we get something that is sandwiched as n goes to infinity. Alright, went through that a little bit quickly. But basically, we take the limit as n approaches infinity of this line. This is going to be sandwiched between two things that do not depend on n, and something that goes to 0 as n goes to infinity. Yep, so that is the proof of Shannon's source coding theorem. Basically, it says that if you're encoding some extension of a Shannon-Fano or Huffman code, right? So remember I showed you earlier that this theorem apply this this was a Shannon-Fano, this was Shannon-Fano, this is Shannon-Fano. This also applies for Huffman codes. I showed you that a little bit earlier. And so for Shannon-Fano and Huffman codes, increasing n reduces the average length of the code word per original source symbol down towards the entropy, and it's truly limiting. Yep. Now, Markov sources. So, we've looked at a bunch of sources, and yesterday we went through Markov sources, and today we're going to go through them quicker, but again. So, Markov sources. For a Markov source, this is basically just a way of taking into account that a code word might appear more frequently after a previous code word, or vice versa, right? So we're taking into account conditional probabilities with Markov sources. The way we do that is with something called a transition matrix. And the transition matrix is just a matrix full of probabilities, but each probability can be written as P of Si given Sj. Okay? So it's just a matrix of these probabilities. We also have this thing called the equilibrium. This is going to be the probability that I shows up, that 1 shows up, probability 2 shows up, and so on, right? In a sense, there is like less information in the equilibrium vector than in the Markov like transition matrix, right? that's a good intuition to have, because it turns out that if you have that intuition, some things later will make more sense to you, yeah? So, more definitions at this part of the course. We have the conditional information. This is the information, but we're putting in a conditional probability into the argument, right? So remember, we had the information at the very beginning of this was minus log base r of p. Here we're just putting p as a conditional probability. All right, we also have conditional entropy. This one, we have a different notation. We have the entropy of S given Sj. When you see a capital symbol, that means you want to sum over all of the entries in that set, right? So that's exactly what we're doing here. We're summing over I, Si, information Si, summing over I, right? So this is, again, I guess you could say kind of natural. Yeah, question?
Real quick, the PIJ, is that saying it's the probability of I to J?
Yes, yep. So that's a really good question. Well, we're using the notation Pij. That just means it's the probability that we see Si given that we have seen Sj. I could also have, so what does this probability mean? Well, let's say we had some message and it was like S1, S2, S3, S1, 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 S2, S1, or whatever. The probability that S3 shows up could be hugely dependent on if S2 has shown up, yeah? So that's kind of what we're trying to describe with these Markov matrices, is how the previous event can impact the next event. Anyway, that's just intuition. Markov entropy and equilibrium entropy next up. So yesterday we said that the Markov length was equal to the weighted sum of the individual Markov length of the individual lengths. That's something that we saw yesterday. This was a sum. Here you have something very, very similar, where the Markov entropy is the weighted conditional entropy of the source. So this is something I think is best to see with an example. We'll do that a little bit later, so I'll make sure to come back to this, yeah? We also have that the entropy of the equilibrium vector is just going to be taking the entropy and you're summing down the probabilities in the equilibrium vector. Again, we will see that in an example. Right now. Okay, so Markov entropy, what you're going to want to do to find the Markov entropy is you're going to want to find the entropy of each column of the Markov transition matrix and multiply it by its corresponding probability in the equilibrium vector. Yeah? In this way, it's kind of like a weighted sum. So I don't want to write all that down. That's why we have these lecture notes. That's why we have these slides, so I don't have to write stuff down. HS1, HS2, HS3, right? So if I want to find the Markov entropy, I need all of these. Then I'm going to weight them with the probabilities in that equilibrium vector. And, well, I also have this equilibrium entropy, which is going to show up, well, pretty much as soon as I'm done with the slide. Turns out the equilibrium entropy, it's just like taking the entropy down the equilibrium vector, is, well, here, it looks like it's greater than the Markov entropy, yeah? And that's actually in general true. So for a Markov source, we have that the Markov entropy is less than or equal to the equilibrium entropy. Remember what I said earlier when I said that the equilibrium vector has less information in it than the Markov matrix? That's exactly what's being said here, right? So let's say I have some day where I know the forecast and the weather matches the forecast. Oh, I'm not very surprised anymore because I have more information. Yeah? So it turns out if you have more information about a system, the surprise factor, which is really what the equilibrium is, decreases. All right, I hope that makes sense, like intuitively. You also have equality if and only if the source symbols are independent of each other. That's kind of like there is no extra information in the Markov matrix, yeah? Because all of the probabilities are going to be the same down the columns. If that doesn't make sense, shoot a question in the chat. Otherwise, I will continue. Here's a gross theorem, or a gross definition, the extensions of a Markov series. Don't worry about it. It's never going to show up. What is going to show up is these formulas, because they let you calculate the same thing in a better way. The Markov matrix. What the hell? Okay. The Markov matrix, you can bring the n down the front. That's what we saw earlier. But it's in general not true for the equilibrium entropy. The equilibrium entropy of an extension is going to be the equilibrium entropy plus n minus 1 times the Markov entropy. Not really an intuition for that one, just kind of a fact. If you really wanted an intuition, you could start thinking about Huffman coding. There is an intuition that you can get from there. It's a little bit too complicated for me to explain in words right now, so I'm not going to, but it's something for you to explore, definitely. Yeah? Limit n goes to infinity. This is directly implied by the theorem, the line above. That good exercise. All right, noisy channels. Oh, yeah. Okay, so noisy channels. What is a noisy channel? Noisy channel is, let's say we have probabilities A1, B1, A2, B2, and we want to send some information from our source across to an output, and in the output we see the B's, and in the input we give them the A's. Yeah? Well, through this channel there can be noise, and it could flip what we interpret the A's to be. So we have some probability that the A shows up as a B1, and well, if it's a binary channel, then you get 1 minus the probability that it shows up. Right? Very simple. Here is a definition, which I will just read out. Here's a definition for like the symbols. So set symbols, we give them the set A. The retrieved symbols, we give them the set B. This one's called a source, the other one's called a sink, and they have all these probabilities. Cool. Just definitions at this point. And well, I'm sad to say that the noisy channel part of this book is a lot of definitions, and then we finally get a mnemonic at the end, and things become easier, but for now, next like couple minutes, it's just going to be a lot of definitions. So, source entropy, HA. We saw that earlier. This is just going to be equal to the probability that A shows up. Sum should be negative. Log, this needs to go away. Log of PA. So there should be a negative sign there. H equals minus log PA, minus sum log PA. Alright. We also have the conditional entropies. We saw these a little bit earlier. Remember, when we see the conditional entropy, it's just the entropy formula, but we're summing over the capital symbol. Right? So we're summing over the set. We have more definitions. We have the noise entropy. So here, we're summing over 2 capital letters. And the way we do it is, well, this is B given A. So we have the probabilities of A weighting the conditional entropys of B given AJ. Channel equivocation is we have the other way around. So it's the entropy of A given we know everything about B. It's this formula, right? Again, we are summing over the B's, and here we're summing over the A's in a different order to what we were doing in the last one. So these are not the same equations. Joint entropy, this one, gross formula. Again, similar to the one that we had before. Don't worry about it, there are better ways to calculate. All right, so noise entropy of H of B given A is a measure of the average information in the output given the input, right? That should make sense. Here we're saying we read this as H of B given A, so what makes sense is this is H, the entropy of the output given we know everything about the input. H of A given B is, we read it as H of A given B, so it is the entropy of the input, given we know all of what the outputs are going to be. Yeah? Joint entropy can be understood as actually the whole information of the channel. It's a lot more intuitive to look at this formula, I think. H of A, this is, I'm going to draw this out with a Venn diagram. This is the information in A. So this is the information in the output, A. This is the information in the output, given we know everything about the input. So since we know everything about the input, it will give us no further information. So when we draw out the Venn diagram, we're actually not going to get the intersection, we're just going to get both of them together. And so that is, I guess that's my intuition at least, for how the joint entropy is given by H of A plus H of B given A. A little bit scuffed, not in the course notes, just a little intuition that I have. And because it's not in the course notes, I'm going to delete it. But we have these formulas, H of A given A and B, and H of B and A. Hey, these are interchangeable. That's true, because the formulas are also interchangeable. Yeah, so we have two formulas for these. We have H of A plus H of B given A, and H of B plus H of A given B. We have this idea called the mutual information. Mutual information. The mutual information is simply an idea of like how interdependent the input and the output are. It's a measure of how, I'm going to use the word covariant they are, you know, just to tease anyone that's taken statistics. So let's imagine that these were independent. Then H of A given B, H of A given B, well, B tells you nothing about A, so that's just going to be H of A. And so the mutual information would be 0 if they're independent. In that sense, the mutual information is a measure of how codependent the output and the input are. And there are two formulas for it. All right, that's a lot of definitions. Luckily, Thomas Britz's notes gives us a handy mnemonic, which is just, well, it kind of looks like a burger. What you do is, to read this mnemonic, all you're going to say is, well, let's just go through an example. So if I wanted to find I of A and B, what I'm going to do is, well, I need to find this block. And I'm going to do it by taking maybe this block and subtracting away this block. Right, so this would be H of, if my pen will work, H of B minus H minus H of minus H of B given A. Let's see how my pen works. We could finger paint. You can finger paint. But we will see how it works if I just shake it up a little bit. That's better. So minus H of B given A. Still a little bit scuffed, but it is what it is. All right. We could also find H of A. We're just summing and subtracting blocks, and each of these layers tells you how big a block is. Yeah. Hopefully that makes sense. If not, try out, see a formula that you know, see if you can build it. All right, so now the rest of this part is just going to be one big example, just to like go through everything. We are a little bit strapped for time because I do need to leave exactly on the dot. We're going to, well, we'll do what we can. So, for binary channels, we have this. We have generally, what we'd like to do is we like to define this little function. This little function is, we call it the entropy of some probability. It's a really neat function because it lets us simplify all of our equations down into something that we can actually write on a page. Anyway, we'll see that it's useful in this question. So, Consider a binary channel which has input symbols A and output symbols B. So we have P of A1 is equal to X. Immediately, before I even read the rest of the question, I'm going to write that P of A2 is equal to 1 minus X. 1 minus X. Now, continuing to read the question, we have P of B1 given A1 equals P of B2 given A2 equals 4/5. Again, immediately I'm going to write out that P of B1 given A2 equals P of B2 given A1 equals 1/5. Okay, immediately I can say that. These maybe should be the other way around to be like more logically consistent with the above line, but it's no big deal. Find the entropy HA. Right, so what was the entropy HA? This was, well, that doesn't really help you, does it? So this was going to be the entropy of A is going to be equal to the probability of A times, well, it's negative that, log probability of A, yeah? A1. A1. And then it's going to be subtract probability of A2 log probability of A2. Yeah, that's just our definition. Well, we have A1 and A2. This is X. This is 1 minus X. I hope you can see, if you look at this formula, just sub out P for X's, you're going to see that this formula is exactly the same. So we're just going to write this as equal to H of X. And that's the form that we're going to leave our answer in. Okay? We also have H of B given A. All right, so there's 2 capital letters here, so 2 summations have to happen. The way that we're going to do that is, well, this is P of A1, the entropy of P of B given A1, plus P of A2, entropy of B given A2. So this is definitely something that we can calculate. So this is X, this is 1 minus X. So yeah, we want to calculate these things now. These are the 2 things that we want to calculate now to end up with our solution. Yeah, turns out you can do that calculation, and you will very quickly see that it is equal to H of 4/5. Right? So our whole conditional entropy is going to be given by X H of 4/5 plus 1 minus X H of 4/5. Those are going to cancel, yeah? Those are going to cancel. We end up with 1 times H of 4/5. And that's exactly what we find. Amazing. So we can see that like using this H function was actually really useful here. This question continues, trying to find the entropy of B and the mutual information. So to find the entropy of B, well, this is just from our what we assumed knowledge for this course. So we can plug that in, and we find this expression for the entropy of B. Right? Don't believe me, you can go through that a little bit more slowly. We can then tell us about the mutual information, because we've already calculated H of B. We just calculated H of B. We already calculated H of B given A. We just calculated H of B. We can subtract them and find the mutual information. Right? And that's exactly what we do here. Again, going a little bit fast. Feel free, pause the recording, slow down, put me on half speed. Feel free. Alright, so final topic is called channel capacity. So channel capacity, all it is that we are maximizing the mutual information by varying the probabilities of the source symbols. Okay? So that's kind of the only definition that you need for the channel capacity. The way that we maximize it is by taking derivatives and setting them equal to 0. Right? So that's the way that it's done in these notes. I'm going to pause on those to let you see exactly how we do it. But there's a better way, at least in this case, there's a better way. So I'm going to write down the mutual information, A and B. This was equal to the entropy of, I think it was 1 on 5th plus 3x on 5 minus h, 4 on 5. Right, this was our mutual information. Now, to maximize it, the only thing we can vary is x here, because that's the only probability in our source symbols. And so we just have to maximize this equation, and our whole mutual information will be maximized. Turns out there's a fact that you can know. But what I'm going to do then is I'm just going to say, hey, this is going to be equal to, so the maximum mutual information between A and B is going to be h of 1/2, because I am only maximizing this term because the other one is constant, minus h of 4/5. And that's our answer. Yep.
Do they have to differentiate in the exam?
Yeah, so in the exam you may have to differentiate, and Thomas Britz has given me a warning of like, hey, make sure that you do the chain rule. So here, if I was to differentiate h of 1/5 plus 3 on 5x, I would have h prime, and I would bring the 3 on 5 out the front, yeah? Easy mistake to make. Don't make it in the exam, you'll kick yourself. All right, so I guess if you don't like this method, or if it doesn't work in general, because it doesn't work in general, we can have a look at how we would do it with derivatives. We'd set this equal to 0. This would disappear. It only happens in this case because there's no other probabilities that are messing with it. You would have to set this is equal to what? Log of base 2 of what is 1 is 0 is like 1. Yeah. So this is set equal to 1. That becomes setting this equal to 2. That becomes setting this equal to 2, which becomes setting 1 on 5 plus 3x on 5 gets set equal to 1/2. And we have our solution as we had before, yeah? Again, going through that pretty quickly. But that's all in the name of finishing off this topic super quickly. So, now Cyril is going to take over for information for number theory and algebra. And yeah.
Alright, do you move it with your hand?
Yeah, I move with my finger.
Nice. Kid named Finger. Okay. Hands up for if you like number theory. Yeah. Woo. Alright. So we're going to do like a bit of revision. Hopefully sound is okay, by the way.
Yeah, sound should be fine.
Alright. We're going to do like a bit of revision on like 1081 stuff. So it's like modular arithmetic. Kind of important. We're just like setting the groundwork. So first, like we have the property of the remainder, the modulus, right? So like say you have like integers a and b, you can always, and if you have like integers q and r, you can write them in this form like bq plus r, which just means that like if your q is your coefficient and r is your remainder, you're basically taking a divided by q and then finding the remainder of that. So here we have q is the quotient and r is the remainder. So after finding the remainder after division, you can write that a is congruent to r mod b. So in this modular space, all numbers which have a remainder of r are congruent to each other. So you can imagine r plus b, r plus 2b, etc. Oh, sorry, r plus q, r plus 2q, and so on. Those are all congruent to each other because they're all like offsets of multiples of q. Cool. So we say like if the remainder is 0, then b is a factor. This is just math, right? If you don't have a remainder, you're a factor. Wonderful. So then you also have your greatest common divisor. So if you are a factor of a and b, that's a common divisor. And if you are the maximum possible factor of a and b, then you are the greatest common divisor. So to find the greatest common divisor, we use the Euclidean algorithm. Again, this is all 1081, but the idea is you have a and b, right? and then you swap. You like in the next step, you swap A with B, and B with R, which is A mod B. So like very loosely and non-rigorously, you would like convert it like that. AB goes to B, and A mod B. Cool. So this is kind of important. Like this is a Euclidean algorithm, but you also kind of, if you aren't allowed to use technology, you might need the extended Euclidean algorithm to calculate the inverse. I think we'll like kind of describe that in this section. The inverse of an element is if you multiply it with the original element, you get 1. So it's like A divided by A is equal to 1. This part of like dividing by A is the inverse. And it turns out like an element A in like modulus M is an inverse if and only if it's co-prime to A. So I say co-prime, that means that the greatest common divisor of A and M is 1, or in other words, the only common divisor is 1, they share no factors. You can kind of see why this is the case if you like take something like 6 and then like find mod 8. Like you can't really take 6 and make it and multiply it by something like k and make it congruent to 1 because like for example they both have to be even. And you know you can say the same thing about any shared factor. It always has to be a multiple of the shared factor. But you can just take this as given. And we say the set of invertible elements in Zm is UN. So just a bit of notation. We say UN means the units. So these are all the elements which are invertible. So we can now perform some like nice operations on like dividing. So note that if M is prime, then everything is a unit except 0. So 0 to -1. Because like the GCD of anything less than M except 0 is 1. So we also introduced Euler's torsion function, or the phi function. So the torsion function is defined as the number of units. And there's some rules for calculating it. Again, 108.1 stuff, yada yada. The general form is like, you want to say that it's multiplicative, so if A and B are co-prime, you can split the product. And if you have a power of a prime, you can write it like this. So, yep. Sure. Where's the mic here? Ooh.
Which would not good. And I'm only capturing the notices as well.
Ooh.
This will be capturing. You know what? It is what it is. It is what it is.
Okay, sure.
It is what it is.
I'll just keep going.
Yeah, just keep going.
I don't know, but yes,
Oh, down here. Do you want to come up and show us? You know, big.
Now, these two are the.
Yeah.
I'm saying, what did you just mean?
Oh, like, yeah, just turn them off down. No.
And we will just check this now. So,
Nice.
Alright, so.
Ooh. Ooh. I love number theory. I love number theory. Yeah. Okay.
It is what it is.
Sure. I'll try and speak okay-ish. So, you use the multiplicative property to separate out the prime powers of 36. So 3 squared times 2 squared. So after you get its prime decomposition, 36 is, actually I wrote it here, 36 is 3 squared times 2 squared. And then you use the p to the a minus p to the a minus 1 formula, which is this thing. Cool. So now we introduce Fermat's little theorem. If p is prime, then for any integer a, which is less which is not a multiple of p, I forgot to add that, whatever, a to the p minus 1 is congruent to 1 mod p. So this is a special case of Euler's theorem, and it's a lot more useful, which is to say a to phi n is congruent to 1. This deals with n in general. You also need a and n to be coprime. So another way to say this is that a unit to the power of phi to the n for any n is going to be 1 mod n. So not just primes. So the order of an element A is defined as the minimum A, so the minimum k for which you can get a to the k is congruent to 1. The way I like to think about this is in terms of cycles. So you're given this totient function property for free. So it's almost like with the totient function, you can say you can have a squared, and so on and so forth, and you go on a cycle until you get to 1, right? So like you're multiplying by a every time. By the pigeonhole principle, you have to eventually repeat, right? So you're going a, then you're going to 1, and then you're going back. So you'll get for free that you can always do this in phi of n, but it's possible you can do it in a smaller cycle length. So this smaller cycle length is called k, where all of these elements here are not equal to 1 until this last one. So this is a cycle length of k. And so the reason why like you can think about this is, well, firstly you say if g, we define g to be primitive if its order, so if its minimum cycle length by multiplying is equal to phi of m. So if this happens, then that means like g, like the powers of g must generate the entire group of the units. The way this kind of works is there's only phi of m units, right? And so if the smallest order has to be phi of m itself, then it must like go through every single one. Like it will go through g squared up until 1, and then it'll have to repeat at g. There's going to be no other duplicate elements, so like every pigeonhole has to be filled up in your unit space, so it generates the entire group. So again, like an interesting property of this is that if you have like your smallest order cycle that goes to 1, yada yada, and then goes back to 1, the cycle length must always divide phi of n. So the order of A always divides phi of n, because you get phi of m for free, and the cycle length must wrap around enough times to get phi of m. So it has to be phi of m has to be a multiple, so you can wrap around and get exactly to 1, because none of these elements here are equal to 1. So this is useful because like what we're all kind of building up to, like you can just memorize the result, which is kind of funny, but what we're building up to is to say that if g is primitive, then g to the k is primitive if k is coprime to the totient. And like a reason, like slight visualization, like slight intuition for this is if you have your cycle, right, and you can imagine you have like an element g to the k on it, if g to the k shares a factor with phi of m, then you're going to stop early when you try and like raise g to the k a bunch of powers. So if you go g to the k, g to the 2k, if it shares a factor with phi of m, it'll stop early. You won't go all the way up to your max. You won't be able to cycle through all of the units, so g to the k won't be primitive. But if the GCD is equal to 1, then you'll be able to like overlap and such, and like get every single element. So in that sense, like it's a unit of the unit space. That's really what a primitive element is. So this actually means that like, this is actually like an interesting case because G generates the entire space of units, and you can say G to the K is primitive if and only if this is true. You actually have a full description of all the primitive elements, which is that the totient function, which again like describes the number of coprime elements, right, will be applied to phi of m again. So if you have at least one primitive element, then you have phi of m primitive elements. Again, the first phi of m is the number of units, and the second phi of m is the number of units of the units in a weird sense. So note that you need at least one primitive element. So for example, U of 12, I'm pretty sure has no primitive elements in it, so you can't apply this phi of m property. Yeah. But usually, like, this is like a classic question. You just need to memorize this formula here. All right. So a field, right? Okay, so I'm like gonna kind of skip this part because there's just a bunch of rules here. Like these are your field rules, all from 1081. Like all they kind of say, so you can see like associativity, commutativity. All these kind of say is that you can do normal algebra in your finite field. Or a finite field is a finite field if you can do normal algebra. So we know that battery? Yeah, sure. If z of p is a field if and only if p is prime. So like mod p is a field if and only if p is prime. You might have come across this in 1081. Unfortunately, stuff like mod 12 is not a field. For you group theory enjoys, it's actually a group product of fields, which is not a field. But it turns out like every other field is a power of a prime p to the n. So the question is how you get this field of prime p to the n. So all the fields which have the same order are isomorphic to each other, so like they're basically the same. And we say like, this notation is important. Field with order p to the n is labeled gf of p to the n. So the question is how we get them. And the answer is right here, leaking off my screen. The polynomials. So you guys know what a polynomial is? I mean, come on. It's a function which is like a sum of powers multiplied by a bunch of coefficients. And we say we define these terms here. So a monic polynomial, the degree of a polynomial is like the number of terms. Monic means like this term here is 1. And more importantly, this term here, the set of polynomials over f is defined as f square bracket s. So this is a field extension. Again, more terms. But all this means is like you have your field of elements, which is like, I don't know, like let's say in the mod space it's like 0, 1, and then something else, I don't know. You just like extend that with the element x, and then you can perform algebra on x as well. Cool. So in saying that, you can actually do a bunch of stuff like division. So when you divide polynomials, you would use polynomial division. We'll see an example. I'll like do like an implicit polynomial division exercise if you guys have like forgotten it. But basically, again, we can write it in this form where you have q is like your quotient, right? Your quotient polynomial, and r is your remainder polynomial. And it always holds that you can always find a construction in this case where the degree of the remainder polynomial is less than like the coefficient. Sorry, the thing you're dividing by, the divisor polynomial. Like same structure as like modular arithmetic. So for linear factors, we can like find like the divisor of a linear, we can find the remainder after dividing by a linear factor. So we can label this as f of c. And we say that if f of c is equal to 0, then x minus c is like a factor of f. And we say c is a root of f. This actually holds in general for like any divisor. If you have f of x is equal to like q of x times like any divisor plus a 0 polynomial, right? This means that d of x, the divisor, is a factor of f of x because you have like the remainder of a 0 polynomial. Again, this is you would calculate this via polynomial division. We say that a polynomial is irreducible if it has no proper factors. So like I can't factorize it anymore into linear or quadratic or whatever factors. The set of polynomials modulo f is defined as zpx mod this like symbol f here. So to sort of give like an intuition for this, like let's say f of x is equal to like x cubed plus x plus 1, right? What the modulo does is you take any polynomial, you find its remainder after dividing by f of x, and then you say all these polynomials which have the same remainder are the same. So this actually means like after you do your remainder, note that you can't ever have like a cubic term in your remainder because the degree has to be less. So all of the polynomials will be of the form of a quadratic, right? Plus c, right? This is kind of important. I'll just write this out. So all of the like reduced polynomials will be at least of this form. And now the reason why this is useful is it turns out that if we take like this set of polynomials over a modulus, it actually gives us a field. So then we ask, how many elements does this field have? Well, if you look at the set of like quadratics you can have, right? Let's say for mod 2, right? Actually, let's generalize this. Each of these coefficients here can be any of p elements because you're dealing in mod p. You have p elements here. And the number of times you can choose from p elements is n. N being like the degree of your polynomial. So you actually have, if you have an n degree polynomial, and you're working over mod p, you have p to the n elements. Lo and behold, that must be the same as gf p to the n. Right? Or isomorphic, I shouldn't say equal, isomorphic. Right? So now we actually like suddenly get all of our finite fields. So like any you can change this m to whatever you want, as long as m is monic and irreducible. I don't know where I crossed that part. So as long as m is monic and irreducible, you can get this property, which is very nice. So a couple of other things. We sort of say that alpha is a root of mx equals 0. So one way to think about this, like this might be a bit of a weird stretch, but if you imagine you have like x squared plus x plus 1, right, equal to 0, it doesn't look like it has any roots. Like you can see like if you substitute 0 or 1 into this equation, neither 0 or 1 appear to be roots. One way to think about this is that you pretend you have a root alpha which satisfies this equation, right? Plus 1 equals 0. You can see alpha squared plus alpha plus 1 equals 0, so you just say alpha is a root. Another way to think about this is that you say it's a root over the modulus space. So you can say like alpha, which you set equal to x. You can see it's like clearly a root because x squared plus x plus 1 in your modulus space is equal to 0. Therefore, like x, which is like set to alpha, is going to be a root. Cool. So the powers of alpha up to n minus 1 form a basis. So that means it covers the entire space of your finite fields. Or like you can take you can take like sums of alpha, sums and powers of these basis elements, sums of these basis elements to get any finite field element. We'll see all of this. And the primitive element G, there exists a primitive element G such that it generates like every other element in your finite field. Cool. So the way you kind of get these elements is by noting that so you'll have like x, like let's say you're working with like a polynomial which is degree 4. You'll get like, you have to force one x squared and x cubed to be all in your space because they all have degree less than 4. But something like this, alpha to the equals alpha plus 1, this comes about from like noting that alpha is a root of your polynomial. So alpha to the 4 plus alpha plus 1 equals 0, and because you're working in mod 2, you can just add alpha plus 1 to both sides to get this property. And you get all of these other rules here by doing more algebra. So you get alpha to the 5, alpha to the 6 by just multiplying by alpha. When you get alpha to the 7, for example, you will get alpha 4 plus alpha cubed. And then alpha to the 4 will expand out into alpha plus 1. So this will just be alpha plus alpha cubed plus 1, which you can see here. Cool. So our question here is to simplify this into a positive power of alpha. So we know that like the powers of alpha less than n are going to form a basis. So like this is actually fine. What we end up doing is we just use this table of stuff here to compress everything into single powers, and then we use subtraction when we're dividing the powers. So to sort of show this, right? I guess I didn't leave out working space, but yeah, I'll just kind of show this. Alpha to the 8 here is alpha squared plus 1. So you're going to get alpha squared plus 1 plus alpha at the top, plus 1 at the top, and then alpha to the 11 you expand out similarly. The same terms cancel out because you're working in mod 2, and you end up with alpha squared plus alpha over alpha cubed plus alpha, you look at your table to find out where these guys are. So you find out the top is equal to alpha to the 5. You just kind of search through, you see, okay, alpha squared plus alpha is there, and you see alpha cubed plus alpha is over here, right? So when you divide through, you get alpha to the 11. So we've simplified it. Oh yeah, one other trick is if you have alpha to the negative 4, it turns out alpha to the sort of 2 to the n minus 1 is equal to 1. So you can express that as like alpha to the 15 times alpha to the negative 4, and then you can add the powers. So we'll see like some examples of this. Cool, and I guess like we want to solve these linear equations here. This kind of just gets messy. I'll show like an easier, oh yeah. Yeah, sure. Alpha to the power of 2 to the n minus 1. Oh, so n is the degree of the polynomial. So in this case, it's 2 to the 4. 2 to the 4 minus 1 is 15. Right, cool. So you can kind of see we stop at alpha to the 14. That's because alpha to the 15 is equal to 1. And this holds for other powers. So if you have a degree 3 polynomial, you'll have alpha to the 7 equals 1. Okay, so I'll just show like the row reduction for this. I'll do a nicer example of this, funny, where like you can use like some funny tricks to solve the simultaneous equations, but this is really just simultaneous equation solving. Like you have like equations alpha to the 7x plus alpha squared, y is equal to alpha squared, alpha, and then so on and so forth. Cool. But yeah, we'll see this in the BCH chapter, some nice examples of this. So there are some algorithms for testing primality, so we'll go through them. So we have the pseudo-prime test, the Lucas test, and the Miller-Robin test. There's one other one, which is trial division. This one, you just go, if you have a number n, you just try every number from 1 to square root n, and then try and divide it. So a secret little test, not really. And I'll also say, yeah, actually we'll leave it at that. Okay, so we have an integer n. So for pseudo-prime test, we have an integer n. All we do is we pick a random number a. If a is co-prime to n, then obviously it must be composite, because it shares a factor with n. So we need a less than n, so we don't accidentally pick n. So if it shares a factor, then it must be composite. Otherwise, if Fermat's theorem doesn't hold, then it must be composite. Note that this isn't like necessary, like this isn't sufficient to prove that n is prime, but it's probabilistic. That's why this is called the pseudo-prime test. Any number which satisfies this is called a pseudo-prime. Then you have the Lucas test, which tries to get a bit stronger. So instead of just testing a to the n minus 1, not being congruent to 1, it also tries to see if there exists an order. So if you can factorize n minus 1 into primes, and then test if n minus 1 divided by p is not congruent to 1, then it must be yes. The answer must be yes. So the answer must be yes if it's not equal to 1 for all primes p, because that means n minus 1 is actually your order, right? N minus 1 is the order of a. The idea is like a to the n minus 1 is congruent to 1 mod p, right? Like if a is a primitive element, then it'll be congruent to 1, and when you take it to the power of n minus 1, and no other factors of n minus 1 will work. You can't replace n minus 1 with any other factor, any of its factors, and make it work. Cool. So again, as I said, this only works if a is a primitive element. Whoopsie. If a is a primitive element, and so this would tell us that n minus 1 is indeed phi of n, and this only works nicely if you can factorize n minus 1. And then you have the Miller-Robin test, which is like an even stronger version of this. So any number that satisfies this test is a strong pseudo-prime. Again, there are numbers which are not primes which satisfy this. So the idea is you like take n minus 1 and you divide it by 2 a bunch of times. Like you divide it as many times as possible until you get t. And then you reconstruct this entire thing, kind of erased it or whatever. So 2 to the s times t plus 1. You choose some random number a from the mod space, and you check if this is true, then it's probably prime. So if a to the t is equal to 1, then it's probably prime. Otherwise, if any possible r, if there is any r from 0 to s minus 1, where this is true, then n is probably prime as well. Otherwise, if none of these checks work, so if you find a to the t is not equal to 1, and like none of these like -1 congruences hold, then it's not a prime. So the probably prime case, like it's like a fall through, it's like a hole in your statement. So in practice, there's very few pseudo-primes. I think like the statistic Fritz gave was like 0.1%. So a more important like factorization method, you'll see this in the exam, is Fermat factorization. The idea is like you use the difference of squares, where if you can find like s squared equals t squared minus n, you can rearrange n as t squared minus s squared, like this. So you'd have like t minus s and then t plus s. And so you factorize it because this is a, this is b. Cool. So we'll see an example of this. So with 2,419, one important thing to note is to try and like, so you can use a calculator, like you can find the ceiling of the square root of n. That's the first number you try. One thing to note is that this is weirdly close to 2,500, whose square root is 50, right? And so one thing you'd want to try is if like 50 squared minus 2,419 is also a square. It turns out it is. It's 81. And so you just reconstruct everything. And you get this thing over here. So you have 9, which is 9 squared, which is the subtraction. And so then you take t minus s and t plus s, which is 41 times 59. Cool. All right. So on to algebraic coding. So we're gonna like use all of our theory about the GF stuff to sort of like tech out our Hamming codes. So consider this Hamming code parity check matrix. It's rearranged in this funky way, and you'll see what it means. So GF8, like let's say like you pick this cubic polynomial here, and you take alpha to be a primitive root of this, right? The columns of H correspond to the coordinate vectors of the powers of 1 alpha, alpha squared, up to alpha to the 6th. The idea is that this would represent 1, this would represent alpha, and this would represent alpha squared. And the sums along columns will give you your powers. So for example, here it's 1, here it's alpha, here it's alpha squared. This is 1 plus alpha, right, which is equal to alpha cubed from this rule here. And then you can extend your exponent like power table to get alpha to the 4, alpha to the 5, alpha to the 6. So you can see here, for example, alpha to the 5 is equal to 1 plus alpha squared. So this will be the 6th column because we're like indexing by 0 because like the first column is alpha to the 0. So all of this is to say like the sum of the alphas, like the powers of alpha, will be covered in this matrix. So we can actually represent H by their corresponding primitive, I guess, root powers, right? 1 to alpha to the 6th. So we're gonna try and use like this algebraic method for encoding stuff. So recall the syndrome from all the way, like in our previous chapter, yesterday's lecture. We're gonna define it differently as a polynomial this time. So we're going to have C0 up to C6 be the coefficients of a polynomial. So this is our code word. The syndrome is going to be applying alpha squared to this polynomial with its coefficients, right? And it's going to give us C of alpha. So this is very important. Like syndrome is like important in like a lot of coding compression stuff. Cool. So this is the polynomial which corresponds to the code word. So C of x is the code word polynomial. All right. So if you have like a polynomial in mod 2 extended with x, and it has degree m and a primitive root alpha, you define n like this and k like this. This is sort of to say like this is the total number of bits like in our message. And k is like the number of information bits, right? This will be the number of check bits. same as like Hamming. So H equals 1 up to alpha to n minus 1 is the check matrix for a binary NK code. So we know that any Hamming code can be obtained this way. So now we introduce BCH. So I'm gonna like superficially describe the details. It's good to see like a rigorous example of this. But we say that this is our code word, right? And as before, as I just said before, m represents the number of check bits. So we say the first m terms in our coefficient polynomial is going to be the check bits, and everything else are the information bits. So you want to choose some m where you have enough space to include the information bits and the check bits, same as Hamming codes, right? So the information bits and check bits are neatly divided. So the syndrome is going to be calculated as alpha applied to this whole thing. Again, if a code word is correct, we want the syndrome to be 0. So we have C of alpha equals 0, right? We want this from a correct code word, right? And we want a syndrome to be equal to 0. So like we want to say like alpha is a root of the polynomial, yada yada. M1 is going to be the minimal polynomial. This is like the whole thing we divide by. Like this is like our modular space, like hyphen / bracket M1, right? Like that. M1 we say is the primitive polynomial of f of x, because like it generates all other polynomials. But more importantly than all of this is like the sort of process for generating the check polynomials. So you'll start off with your message, which are your information bits. These look like this. Now to get the check polynomial, we need some bits from C of 0 to C of m minus 1, right? We need to choose these coefficients so that alpha is a root of our polynomial. Right now, like we have no guarantee that alpha is going to be a root of I of x. So we choose C of x, or we choose R of x, which is our check polynomial, such that it'll force it to be a root. So all we do to do that is we say I of x, we take I of x mod m1 of x. So this will like force it to be a root. Because like when you add the two together, you'll get 0. So this is the important step. So you take I of x mod m1 of x to get the check polynomial. And this is a bit scuffed because you have to do polynomial division. Well, I'll like show this again. And the code word is the entire thing with the check bits and information bits combined. Right, nice on time. All right, so when we try and decode this, we might get some errors, right? So we've calculated our check polynomial, we've got our information polynomial. When we try and calculate the syndrome, we'll get some errors, right? So if there's one error, we'll get something in the place of alpha j, so a to the j. So you can imagine like, let's say you receive a vector d, which is like the original code word with like one single error in a single place. This could be like, like you can imagine when you expand out the sum for C of alpha, you would have like C of 0 times x to the 0 or alpha to the 0 plus so on and so forth. And then when you get to j, you would have C of j, alpha to the j, plus like one error, right? Okay, this is a bit scuffed. Oh wait, other way around. Is there an eraser?
There's an eraser right to the door.
Nice. The error will occur on the coefficient, not on alpha. So you'll have C of 6 plus 1 times alpha to the 6, and so on. So the C of 6 alpha to the 6 term will be grouped with everything else, and the alpha to the 6 term will expand out in the plus 1 factor. So this whole thing will expand out into C of 0 alpha 0 plus C1 alpha 1 plus so on. And then at the very end, you'll get an extra alpha to the j term. So when your syndrome doesn't give you 0, you go, uh-oh, there's an error. That's going to be alpha to the j. So then you ask, okay, how do you correct this error? Literally by setting alpha to the j. If you know there's a single error, you know it's in the jth slot. So like you just set it the other way. Sorry, the j plus 1th letter, because everything is 0 indexed. Cool. If the syndrome of a code word we received is 0, there's no error, as we just said. And important step, I think like this is like a classic mistake. When you decode a code word, like you only want the information bits, so make sure you only take like c to the m up to c to the n minus 1. Don't include the check bits in your final answer. Yeah. Cool. Now for 2 errors, and this is like mainly the reason why BCH is so cool and awesome. For the single error case, we only have one syndrome. This is not enough to tell us where the place of 2 errors are. And this is where it gets a bit complicated. I'll probably like show methodology more than anything. If you have a prime p and beta is a root, then like beta to the power of p to the I is also a root. So we say this is like the powers which are generated by this are called the cyclotomic coset. So I think like best way to show this is with an example. Is there a nice example here? There is not. Okay. So if you consider this field here, the cyclotomic coset of 1 is going to be 1 times the powers of 2. So it's like 1, 2, 4, 8. Actually, I've written it here. For the cyclotomic coset of 3, it's 3 times the powers of 2. So it's going to be 3 times 2, 3 times 4, and then 3 times 8, which is going to get to become 24. And then like in your mod 15 space, this will get reduced to 9. Because remember, everything is mod 15, because like alpha to the 15 is equal to 1. So you take everything mod 15, or like 2 to the n minus 1. Okay. And this is kind of useful because if you have only alpha as your root, you define a second root for another minimal polynomial, which is something that's not in your original cyclotomic coset. So we choose 3 in this example. So we have alpha squared, alpha to the 4, and alpha to the 8. But then we want to choose another power because we want 2 errors to be decoded. So we choose 3. So we choose alpha to the 3 and generate its cyclotomic coset. The use case of this is that you have like another minimal polynomial, which you expand out from this. So this is x minus every like cyclotomic power of alpha. And it expands out to this. So now you have 2 minimal polynomials, m3 and your original m1. m1 was like x to the 4 plus x plus 1. When you multiply them together, you get like your final m of x. And now this is like your new m of x. When you're decoding 2 errors, you want to use this m of x instead when you're like finding remainders and stuff. So we'll see this. We will see this. So now like you have your check matrix, which is alpha, but you also have alpha to the I. I being your index that was not in the original cyclotomic coset. So in the previous example, I was equal to 3. I equals 3 in the previous example. Cool. And the syndrome is going to be this vector that you get. So now we have 2 syndromes. And so the sort of methodology for this is that firstly, when you're encoding, you now take mod of m of x, not m1 of x, not your original polynomial. Like this polynomial, which is like the product of the 2 original polynomials. More theory. And so now, like, I guess it's kind of important. Like, if you have 2 syndromes, right? So if both syndromes are 1, then you know there's 0 errors. When there's 1 error, alpha j plus alpha L, right? Like this result here, and alpha ij plus alpha il, right? Which like comes from like the expansion of this. If this one is like not a power of the other one, then you only have 1. Or if one is the ith power of the other one, then you have 2 errors. So in the case of 3, if this syndrome S1 here cubed was equal to S of I, then that means you have 2 errors. Sorry, that means you have 1 error. But otherwise you have 2 errors. And so the methodology for 2 errors is that you first find like all pairs of a to the j plus a to the k, which satisfy the first syndrome. And then you filter out the ones which satisfy like alpha to the 3j plus alpha to the 3k, which satisfy the second syndrome. Try not to divide by alpha to the I, like that might be kind of tempting, but you'll like lose information. You want to preserve this equation here, like find all pairs and then test all values. All right, let's see, hopefully an example. Okay, all right, exam question. We want to express alpha to the 10, alpha to the 11 as linear combinations. So this is like classic, I guess like finite field stuff from before. So you would use your table, right? You can see here we're given this table. It's not filled out. So we want to extend this table, right? We don't know what alpha to the 10 and alpha to the 11 are. So the way you extend it is by using previously known results. So alpha to the 10 is equal to alpha times alpha to the 9. This is just showcasing how you generate a table by yourself. You see alpha to the 9 here is equal to alpha cubed plus alpha over here. You multiply it by alpha, and you get alpha to the 4 plus alpha squared, and then you expand alpha to the 4. Again, you just keep on using a table to like substitute powers. So alpha to the 4 equals alpha squared. Alpha to the 4 equals alpha plus 1. Alpha to the 11, you do the same thing. You multiply by alpha. This time you don't need to do any substituting because every power is under 4. Cool. So now we've filled out our table, right? We have like everything. An interesting thing to note is that because like alpha is a generator, you're actually going to get like every single polynomial in g of f p to the n. So you get all of this, right? And so the next part is to solve the linear equation in f. So again, you can row reduce, but I'm going to like show like a cheat method. I actually think this might be slightly more inefficient, but basically you have like a set of linear equations. If you look at the second one, your linear equation, you can factorize out alpha cubed like this, and this will be equal to alpha to the 8, right? You can divide both sides by alpha to the cubed, and you get x plus y equals alpha to the 5, right? Like this. And you can see I kind of did this here. So you get x plus y equals alpha to the 5. And then what you do is like you kind of clobber the first equation with that. So you get alpha squared x plus alpha to the 4 y is equal to something, is equal to alpha to the 4. I'm going to separate out alpha to the 4 in terms of alpha squared. So we know alpha to the 4 is equal to alpha plus 1. So this whole thing will become alpha squared y plus alpha squared plus alpha plus y, alpha squared plus alpha plus 1 times y, which if we go back to our table, alpha squared plus alpha plus 1 is over here, so alpha to the 10. So then we expand all this out into alpha to the 10, y is equal to, what was it, alpha to the 4, like this. So now you can clobber this out, and you get like alpha to the 7 plus alpha to the 10, y equals alpha 4. So you can see the working out I've done here, exact same equation. So now you can rearrange. So again, this is just an exercise in substitution. You simplify alpha to the 4 equals alpha plus 1, and alpha to the 7 equals whatever. And you get alpha 10 y equals alpha cubed. You divide, you have this alpha to the negative 7. Again, you notice alpha to negative 7 equals alpha 15. Alpha 15 times alpha negative 7, so you do the math. From here, you get y equals alpha to the 8, and you get x equals alpha to the 4. Feel free to verify this by substituting it in to your matrix, and then like seeing it adds. Cool. So here's a doozy. Now we're actually going to show like how to encode and decode messages. Cool. All right, I think I should just get stuck into this. So, like I say here, like if you're allowed to use technology for the exam.
Yeah.
Okay.
Everything except like a messaging app.
Okay. Then you should really use a programming language. I recommend Python or Sage. Anything works, really. This is a bit scuffed. The process is basically like, okay, so we want to encode this, right? This is our information bits, right? So it's going to start, so you can see here they've given like your information polynomial because Brits is such a nice guy. The bits are in the order from 8, 9, 10, up to 14, right? So these represents which coefficients you should choose. So this will be c to the 8 is 1, c to the 9 is 1, c to the 10 is 1, c to the 11 is 0, and then you get c to the 14 is 1, right? So to write this out, you are taking x to the 8 plus x to the 9 plus x to the 10, right? Scroll. Plus x to the 14, yeah. And notice we want to take this mod m of x. M of x is the product of our two polynomials, which are our two roots, which we use to calculate two syndromes. So we want to take this mod x to the, wow, okay, that's scuffed. The way I'm going to do this, I'm going to like implicitly polynomial divide by noticing the differences in powers. So the polynomial division step is you take your divisor polynomial and you multiply it by a bunch of powers, or you multiply it by power and then subtract, and then you keep on doing that. I don't care about the divisor, I just want the remainder. So I'm just going to note the differences in powers. It's going to be -1, and then -2, and then -4. All right, so if I multiply it by alpha to the 6, I'm going to get like, I'm going to get out x to the 14 first, which is going to cross this out, and then I'm going to get 13 and 12, right? So those were our differences of 1, and then I'm going to cross out the difference of 2, which was x to the 10, so I'm going to cross this out. I'm going to include x to the 9, x to the 9, x to the 8, and then we had a difference of 4 from the difference of 10, which was x to the 6. Cool. And then you just keep on doing this. So now you cross out x to the 13 by multiplying by x to the 5. So you divide this out, and you have x to the 10. You keep x to the 9, and then you subtract by 2, so this gets crossed out. And then you keep alpha to the 6. Wow, I've already lost track. Okay, alpha to the 10, alpha to the 8, and then I'm pretty sure you get x to the 6 and x to the 4. Okay, let's hope I did this correctly. I can see my working out later. So now you cross this out, you get x to the 8, x to the 6 died. I'm starting to think this is not correct. And x to the 4 should also die. Okay, I definitely did not do this correctly. Oh, it's over. Okay, wait, let me just show the working out. I didn't do it. What? Okay. Okay, the end result should be this. Wait, let me see if I can retrace my steps. 14, 10, okay, so you get 13, 12, and you get 10, and then you get 9, 8, and 6. Okay, that's good. And then you cross this out, 13, 12, 10. Oh, what? What am I doing? Sorry. So you cross out 13, 12, and then you get 11, you cross out 9, you keep 8, and then you get 5 and 6, like that. X to the 5 plus x to the 6. Okay. And then you cross out 11, you get 10, 9, and then you keep 8. Here we go, this is more like it. And then you also get a 7, and then you get a 6, and a 5. And the next cubed. Take it out and put it back in. Okay. I'm gonna take it out. Pretty sure this is right so far. Okay. Okay, yeah, this looks good. Okay. Wait, I feel like I'm missing some terms. Oh, yeah, you have like an x3 here. Okay, and then I think like your final step is going to be like, yeah, this looks good. So then you would like cross out x to the 10, x to the 9, x to the 8. You'd keep x to the 7, cross out the x to the 6, and then you'd have a difference of 4 again, which was when you crossed out x to the 6. So you keep x to the 5, x to the 3, and then you also have an x to the 2. So you have x to the 2, 3, 5, and 7. It's okay if you didn't understand this, because this was sort of my own ramblings. But the point is, like, I'm kind of like implicitly dividing by like taking differences. But yeah, you can. If this is to show if like your computer dies, you can just polynomial divide. And you don't have to do like the full step of getting the divisors. You can just keep on subtracting by multiples of the divisors following it. So anyway, you get x squared, x3, x5, and x7. So notice that this means that x0 is 0, x1 is 0, x squared is 1, x cubed is 1, x to the 4th is 0, x to the 5 is 1, x to the 6 is 0, and x to the 7 is 1, right? So we're going to append this bit string here onto the beginning of our code word, which is going to be up to there, right? So these are our check bits. These are our check bits, right? And then the rest of this is our information bits, right? So to recap, we took our information bits, we say we want the syndrome to be 0 when we sub alpha, so we take it over a mod. We take over mod m with polynomial division here, and then you get our check bits. You combine the check bits and the information bits, and you are reaping rewards, because this is your code word. Nice, so I think we're good on time. Now, to decode a message, we should calculate our syndromes first. So, notice our two roots. Remember our two roots are alpha, but also alpha cubed. Because 3 is not in our cycloatomic coset of 1. So, if we calculate our syndromes, we are literally plugging in this entire polynomial with alpha. So what we would calculate is C of 0 times alpha to the 0, which is 1, and then 1 times alpha to the 1, which is alpha, and then alpha squared, then alpha cubed, then alpha to the 5, alpha to the 4, right? 0, 1, 2, 3, 4. You add all of these up, so alpha to the 4 is alpha plus 1, so I'm pretty sure you just end up with this. Well, let me see, I'm cheating. Nice. So you get this and this crossed out, so you get alpha squared plus alpha cubed equals alpha to the 6. This is our first syndrome. Our second syndrome, and maybe the step you might have missed, is when you sub in alpha cubed. So you get alpha cubed plus alpha to the 6 plus alpha to the 9 plus alpha to the 12. Again, you use your table, you look up everything. I think I demoed looking up the table, but it's a bit of a scroll. So I'm just gonna show here, right? Okay, you can trust me when you get the table. When you use the table, you get 0 as the first syndrome, and alpha to the 6 is your second syndrome, right? And you can see here our form of having the second syndrome be a cube of the first syndrome is not the case. Alpha to the 18 is not equal to 0. So there must be two errors, right? If it was alpha to the 6 and alpha to the 3, 18 is 3 mod 15, then there's only one error, but that's not the case here. Cool. So now how do we go about this? Whoa, okay, that's a nice step. I'll do stuff on here. The idea is you want to find alpha I, let's say alpha j plus alpha l, which is equal to alpha to the 6. It's equal to alpha to the 6. And you also want to find alpha to the 3j plus alpha 3l is equal to 0. Because it's in mod 2, another way to say this is that alpha to the 3j and alpha to the 3l are the same. So we want to try pairs, which is equal to alpha to the 6. So the first thing you would try is if j is equal to 0, right? And then l is equal to something. It's not equal to 6, because alpha to the 0 is 1. Just be careful of that. So, okay, let's go back to our table, yada yada. Okay, so we have alpha to the 6 is this. If it's 0, then you have 1 plus alpha cubed plus alpha squared. That's alpha to the 13. Unfortunately, alpha to the 6 to the 3 is equal to alpha to the 18, and alpha to the 13 to the 3 is 39. This is 3, this is 9, because you're taking mod 15. Alpha to the 3 and alpha to the 9 are not the same. So then you try another pair. Let's try j equals 1, in which case alpha plus something has to be this. That'll be 11. So right, in this case, L is equal to 11. So if you try 1 and 11, you actually see this works, because 1 to the 3 is 3, and 1 times 3 is 3, right? So alpha to the 1 to the 3 is equal to alpha to the 3, and alpha to the 11 to the 3 is also equal to 3, because 33 mod 15 is 3, right? So now we found a pair. That means our two syndromes, right, must be at alpha 1 and alpha to the 11. So our pair was j equals 1 and j equals 11 over here. Wonderful. So that means that in the second, 0 indexing, and 12th positions, you want to flip the bits. That is done like this and this. Therefore, you've corrected the two errors. We're assuming there's two errors. Hopefully not too many cosmic rays. And make sure when you actually decode it, you exclude the check bits. You only include the information bits. So a decoded message is going to be this. Fantastic. And that introduces us to cryptography. Do we have any questions or anything? 15 minutes. Perfect. All right. Cool. Yeah, not much to say on this. Like, yeah, feel free to revise. I think like examples really help with this. Like, the more examples you see, you'll be like, oh, that's how it goes. That's how this whole spiel goes. And you just memorize it. But I encourage understanding as well. Okay, cool. Let's talk about encryption and decryption. So this is a reversible process. If you decrypt an encrypted message, you should get the original message back. We assume like cryptanalysts, they know about the design of an encryption, but like they don't know the key. So like they will kind of want to like reverse engineer either the key or the message, given like a bunch of messages and keys. Or maybe they want to like, they have a bunch of keys and they can brute force them and get the message back. That's another thing that happens. So we define some stuff. So one possible cipher is the substitution cipher. You either replace it with like a random letter, or you replace it with a permutation of the letters. You don't permute the message, you permute the letter set and then substitute it. So like you could have A go to B, and then B go to Z, and so on. And then this would be like a permutation, right? Like A to B, and then this bottom part here is a permutation. So there's 26 factorial possible keys, because there's 26 factorial possible ways to permute the letter set. Yeah, combinatorics. And for encryption, you apply, given a particular letter, you apply the permutation of like that letter, right? So like A with the permutation applied would go to B or Z or whatever. And then to decrypt, you apply the inverse permutation. Cool. And a transposition cipher is like an actual permutation of the message. What you do is you divide the letters into blocks of length R. So you'd have like your message here. This is block 1, this is block 2, etc. And then you permute these two. So the permutation matrix is given like this. The top row tells you the original position, and the bottom row tells you the next position. So this means the first thing goes to the second place, the second thing goes to the fourth place, etc. So it permutes the letter set in a block. All right, and we can combine these two ciphers to make the code harder to break, which we will see an example of. But we also introduced the visionary cipher. The visionary cipher is a bunch of Caesar shifts applied to offsetted positions. So like, the idea is like if I have like a bunch of letters here, let's say this is a block of R, and then I have a bunch of letters here, let's say this is another block of R, I apply all of the firsts in these block of R's, right? So after you go to this, you go here. I'd apply like a Caesar shift of 1, for example, which shifts the letter by 1, cycling around. This would shift it by 5. This would shift it by 7, for example. Whatever. Point is, you have like R different shifts. R shifts. And you apply them in like periodic fashion. So our method to like kind of break the visionary cipher is Kasiski's method. This is used to estimate the length of a key. And to do this, we sort of define the index of coincidence, which is a probability estimate of how likely two randomly chosen letters are identical. So the idea is like, if we like sample a bunch of letters from our message, and then take like the probability coincidence index, and then like plug it in a formula, we'll get a key length. So to see this, the formula for the incidence, index of incidence of coincidence is the sum of the frequency squared minus n over n squared minus n. This kind of comes from there's n times n minus 1 ways of choosing pairs of messages, of choosing pairs of letters over 2. And then this top part here is like the number of ways to choose letters from the same group of letters. So this frequency here kind of encodes that. The actual expansion is like fi times fi minus 1 over 2, and then you sum that up. And then you divide it by n choose 2. Cool. So the formula that I just described is after you calculate the index of coincidence, you apply this beautiful thing here. This is like actually kind of well reasoned. This comes from the ways to like choose, like in two cases, you can either choose letters with the shift point sort of coinciding, so they have the same shift. So if you remember our blocks, right, of letters, so say you have a block of 4 and a block of 4, the probability like two things coincide is either they coincide and they have the same shift, which is a bit more likely than in the case where they coincide but they have different shifts over here. So there's like this sort of misalignment in probabilities. So this case is a bit more likely than this case. So then you like combine everything and rearrange, and you get and you get this formula here. Cool. So here we have an example, a question of using Kaczynski's method. You literally, so once you to calculate the index of coincidence, you take this entire thing here and then you plug it into your formula. Fun times. So you know n equals 51, and each value of f of I can be found in the table with the letter frequencies. So like f of a is equal to 2 plus 3 equals 5. Just wanted to show that. Over here. Right. So then just plugging in this formula with like every single value, you get this entire sum of squares divided by 51 squared minus 51, and therefore you calculate it to be this thing here. I don't know if they give a decimal. Yeah, there's a decimal value here. So now you plug it into this formula here. Right. And so that'll give you a key length of approximately 2.82. Right. So the second part of this question, The second part of this question says like, given r equals 2, so like r is pretty much 2. 2.82 is close enough. Yeah. We must find the key and decipher the message. This is sort of just like brute forcing like the possible shifts. Some ideas are like, you can look at trigrams like this. You can look at single letters, or you can just like try every single Caesar shift. Like you can try Caesar shifting the first, like every odd element because it's 2, right? You could like try shifting this, this, and this, and then you could see like this, like after some point this gives like a meaningful message. Another way is just to guess that this is probably I and then go from there. Cool. I or A. Yeah. So, in a new form of cryptography, which is asymmetric cryptography, you don't have a common key anymore. In this case, you sort of share keys, and then you perform like operations. You have two separate keys, and then you perform operations to share them. So for RSA, sort of like quickly going through this, you choose two large primes n, and find n equals p times q. The idea is like n is hard to factorize, so you only share n when you're calculating modular stuff. You choose a random element between 1 and phi to the n, and you need the e to be co-prime to phi to the n, so that you can find the inverse of e, right? So you have e and d, where e to the d is congruent to 1 mod phi of n. The idea now is that if we encrypt our message with n to the e, right, it's a bit hard to it's hard to like reverse engineer, even if we know E, what the original like message was, because we have to raise it to the power of D, and D is difficult to find. So the encryption is going to be we raise M to the E mod N, and the decryption is we raise the ciphertext C to the D mod N. The idea is if you raise something to the power of M to the E, and then to the power of D, this is equal to M to the power of ED, med student. ED is common to 1, the mod phi of n. Phi of n is the modulus of like your exponent space. So you can see the results derived here. Cool. So this is just encryption, decryption. Just need to know the formulas. Right. So here we have our favorite Fermat factorization again. So I guess in this case, like, you just use a calculator and you get like the ceiling of the first number you want to try for like the square is 122. And when you get up to 124 squared, you'd find like 729 looks like a square number. Again, you can use a calculator to do this. So you get it's 27 squared. And then you use difference of squares to get the factorization. All right. And now to do the encryption step, we calculate phi of n, like so. So now we know the factorization. Phi of n is easy to calculate. We choose E, and you can use the extended Euclidean algorithm, or you can use, like, because you're allowed to use technology, like, you can just find the inverse, right? So you find the inverse of this is 7, right? So that's your D. So you have your pair, your private key and public key pair. So the public key is E, the private key is D. Right, so it's 1, 2, 3, 4, 3, and 7. Now you find your decryption constant. Yeah, okay, you did that. So now we want to decipher the code 4729. So you do that by raising it to the power of 7, getting this result, and calculating it mod n. And like you get some number in the end, and you don't know how to turn this into letters. If you look at the exam question, it actually tells you how to turn it into letters. Basically, you take like a linear combination of 23 squared, 23 and 1. And so that'll correspond to like 22, 1 and 2, 22 when you try and unpackage this. And then you just look it up on the table of letters, which is EA. Cool. So the final thing we'll cover is unicity distance. Unicity, yes. So this represents like the minimum amount of ciphertext you need to like meaningfully decipher your message if you like try every single key. The sort of idea is like you could try every key, but like if your ciphertext is really small, you might like get like a bunch of garbage messages which like you don't really know if they're a thing. So you need like your ciphertext to be long enough to get a meaningful decryption. The idea is like the number of I believe the number of meaningful decryptions is something like q to the h2k minus n times d of n. So this represents the amount of total information in the total set of keys, right? So your keys derive some information, right? And you don't want too much, like there could be various possible like meaningful messages, but then d of n is your redundancy, and you subtract n times d of n, which is your total redundancy. So this is just intuition, but like this part here means that if this is less than or equal to like, if this part here is like less than or equal to 0, so if h to the 2k is less than or equal to 0, less than or equal to n times d of n, then you can probably get a nice decipherment, because like your exponent will be negative, so it's going to be less than or equal to 1, so there's only at least one possible message, one like meaningful message, right? If it's the other way around, if it's greater than or equal to, then there's like many possible meaningful messages. So if you rearrange the formula, you get this. So this is just plug and play. In fact, there's a nice approximation of this, which is that for English text, if all the keys are likely, then you just have to calculate log base 2 of k. All right, cool. So we have a product cipher, which is formed by applying a substitution and then a transposition. So a substitute, so it first asks for the number of keys. The number of possible keys for a substitution is 26 factorial, right? And there's n factorial possible ways of permuting like a transposition of length 9. We saw these formulas before, so length 9 here. So you have blocks of 9 and you have n factorial possible keys, and you have 26 factorial ways to get a substitution sort of plug board. So the set of possible keys is just the product of these two. The unicity distance, it's very easy. You just plug it into this formula. So I will say like this is like a weird number. You kind of like one idea is to get the log base 2 of 26 factorial and 9 factorial. You can like, you notice they're a product of stuff, so you can expand them into a sum. So you'd get something like log base 2 of 26 plus log base 2 of 25, etc., etc. It's a bit long, but whatever. So now, a very easy question. It says, well, if you know like the theory, I will say, and if you solve the previous question, it says a message of length 50 is enciphered using the product cipher, and it's intercepted by Eve. If Eve tries all possible keys, good luck with that. Would Eve be able to find a unique and meaningful way to decode the message? And you find that 50 is greater than 33.4. So you're more than the minimum possible ciphertext length you need to meaningfully decode this message. So if you look at this, you see 50 is larger than 33.4, so Eve should be able to do it. Eve. Yeah, so pretty simple question. This part of the course is literally just like plugging in formula, plugging in numbers into a formula. So yeah, that's pretty much it.
Oh yeah.
Cool.
Yay, congrats.
Yay. Alright. Good luck with the BCH stuff. I think that's like the hardest. But
Yeah. Alright, well, let's end stream then.
Yeah, I have a quick thing. It's
Yeah.
not all of this, it's just here's a couple of